think we're ready to go. I think we're ready to just jump right in. Bill, we are just really glad you're here and looking forward to, I have some uh, previous, sort of layman's knowledge of climate science and gets me by. And I also imagine that I'm pretty Swiss cheese, right? I got these big holes. I didn't take environmental science in college. So glad you're here to just give us that sort of refresher for those of us that it's new, kind of opening our minds to that, and those of us who know most of this or some of this, that there's an opportunity to go, aha, oh yes. So I'll turn it over to you.
Thank you all. I'm so appreciative of this opportunity to meet with you. I see some friends in the audience. Nice to see you again. I am aware that you are all very committed to this movement to address climate change, that you already know quite a lot and don't need to be convinced that climate change is real and it's a threat to humanity. So my goal today is to arm you with some knowledge and some tools that you might be able to use as you go out into the world and try to move the needle on how society is treating our world, how we get our energy, how we use our energy, and how we can address this problem of climate change. I want to explain a couple of things here. First of all, I have multiple screens here and I have to look up to see all of you, but I'll try to keep my eyes on the camera. And I guess that's it. I'm ready to get into this talk. This is the structure of the talk. First of all, oh, and I wanted to correct something. Sorry. In the bio about me, it said that I had training in climate and meteorology. I actually had a degree. My first degree was undergraduate in meteorology with a lot of training in climatology. I continued on. I only worked for me as a meteorologist for 2 months. I continued on with a graduate degree in computer science, and that was my career. But I always loved the science of climate and meteorology, and I took the opportunity to use that knowledge, that experience, that training, dust it off around 2005 and start becoming an activist. I learned about climate change when I was a student in the 70s, but at that time, it was still a debate among scientists about what impact it would have. The science of climate was known for more than 100 years at that point, and how climate change would be affected by carbon dioxide. But the scientists were still debating about what it meant for humanity. So I didn't pursue that. I watched from the background as the interest and concern grew until about 1980 when James Hansen spoke to the legislators and convinced them that we needed to do something. And it actually started to take off. We saw that uh, the first President Bush, George H.W. Bush, was actually campaigning on the need to do something about climate, but did not have a receptive legislature. We actually saw in the early 2000s when a bipartisan movement to do something about climate happened, and we actually had Nancy Pelosi and Newt Gingrich do a commercial together where they said to America, we don't agree on much, but we agree on this, that this climate change is real and we need to do something about it. But in the late 2000s, around 2008, 2009, at the time that An Inconvenient Truth came out, the fossil fuel interest kicked into high gear with a PR disinformation campaign and really put us behind the eight ball in terms of doing something about climate. And that's when I decided that I could not sit back. I had to take my knowledge and training and dust it off and do a lot of research, because when I was a student, there wasn't a lot of talk about climate change. But I did a lot of research and caught up on the science, and now I'm going to try and present some of that to you today. And I became involved, as all of you are doing. So first of all, the most important thing is to understand that the worldwide environmental energy balance is changing. And I talk about this as an energy balance, and you'll see in a minute why I'm calling it a balance. And what does this mean for humanity? What can we do about it? And what is the next step that you all can take? To begin with, I like a little bit of humor. This is a Gary Larson cartoon where grandma's on the floor. The kitchen is suffered a huge explosion. Everything's in disarray. And on the floor is a cookbook that grandma's been using called Recipes for Disaster. What we are doing, the chemical experiment we're doing in our climate, in our atmosphere, is a recipe for disaster. The way we live our lives, the way we get our resources, and the things that we enjoy so much that we get from abundant energy are a recipe for disaster. So first of all, it's important to understand that almost all the energy on Earth comes from the sun. And it comes in constantly streaming in at a huge amount. It is far more than all the sources of energy that humans create from by digging up fossil fuels, by using uranium, by tapping into geothermal energy and so on, is a very small fraction of the amount of energy that comes in from the sun. As that energy streams in from the sun, it comes in as short wavelength visible light primarily, and that goes through the atmosphere transparently. The atmosphere is like clear glass to the incoming sun, except for some reflection off of clouds and some scattering that occurs. The energy tends to flow in. It hits the Earth's surface and warms the surface, and that warms the air, and that air warms the oceans, and so on, and provides the environment that we enjoy. If all that energy stayed on the Earth and never left, in time, and not very much time, the Earth would be as hot as the sun. Think about that. It would be as hot as the sun. So all that energy that's streaming in has to stream out again. Now, after it heats the Earth, the energy radiated from the Earth is a function of the temperature. Just as the energy from the sun is a function of its temperature and comes in as visible light, the energy from the Earth leaves as infrared light, a much longer wavelength, and a much different interaction with the chemistry of the atmosphere. Now, suddenly, the major components of the atmosphere, oxygen and nitrogen, still are transparent, but the greenhouse gases like carbon dioxide, methane, fluorinated gases, I'll call them F gases from now on, and other elements of the chemistry of the atmosphere, they absorb that heat. They are opaque to that energy. As it's trying to stream out at the speed of light, as radiation always does, it only goes a short distance, about one meter, and it runs into a molecule of greenhouse gas. It causes that molecule to warm up, and then that molecule radiates its energy back out because now it's got more temperature. It's going to radiate that energy. That energy gets radiated in all directions, not just straight out to space. So some of it gets radiated back down to Earth, some of it gets radiated to the sides. And then like a metal ball and a pachinko machine, if you know what those are, a pinball machine, it's just bouncing around in a process called re-radiation. So you have a bit of radiation, it warms up a molecule, that radiates again, it warms up a molecule, it radiates again, until it reaches a point high enough in the atmosphere where the greenhouse gases become thin enough that it can finally escape at the speed of light out to space. The longer it takes, the more re-radiation that occurs, the higher the temperature on the Earth. If there were no greenhouse gases on the Earth, the temperature of the Earth would be like a rock in space, like the moon. The average temperature would be about 0 degrees Fahrenheit. That's physics, straightforward calculation. With the introduction of greenhouse gases, the amount of energy that is retained warms the surface of the Earth up to an average of about 57 degrees Fahrenheit. Substantially warmer, and it makes it possible for liquid water to exist on Earth and for all of us to make this our home. Now, you change the chemistry, you change the thickness of that opaque layer, and you slow down the flow of energy out of the Earth, through the atmosphere, out of the Earth. I have a picture here that's kind of like a beaver making a dam in a stream. And that's kind of the way, that's an analogy I want to use for the energy that flows from the sun to the Earth and back out to space. The atmosphere, the greenhouse gases that are beneficial, that raise that temperature to 57 degrees, they slow down the flow like a dam in a stream and cause a reservoir to build up behind the dam. That reservoir of energy behind the greenhouse gas dam should be 57 degrees, but we keep adding sticks to the dam. Like a beaver, we're busy adding sticks all the time. We're adding carbon dioxide, we're adding methane, we're adding F gases, and we are slowing the flow of energy out. The more we slow that, the more that dam, that reservoir, we're making the dam higher, that reservoir gets higher. Now, as you can imagine with water, if you have a permeable ground around you, or if you have an island in the stream, that island starts to become inundated with that higher reservoir, or the water flows through the ground and comes out in other places that are low. And in the same way with greenhouse gases, we have energy flowing out of the air and into the ocean. We have energy flowing in a lot of different ways, trying to reach a new equilibrium relative to the amount of greenhouse gases that we're having in our atmosphere. Now, we don't stop at a certain level. We just keep adding, and that's really the crux of the problem is we just keep adding. So we're chasing a moving target as we try to address climate change with mitigation and adaptation and resilience. I wanted to just throw this bit in here just to demonstrate how long we've known about climate change. In 1856, Eunice Foote, a brilliant woman, had done a little experiment where she had a jar full of greenhouse gas, carbon dioxide, and a jar of normal gases. And, at this point, science was really beginning to understand and learn about the different gases that comprise the atmosphere and the effects of radiation on those gases. And she measured that when you have sunlight passing through a jar of ordinary air and a jar of carbon dioxide, that the one with the carbon dioxide warmed up. So we've known about this for a long time, and in the late 50s, we started to measure the amount of carbon dioxide in the atmosphere to see how much risk we had in terms of putting the energy out of balance. There is a chart here, I thought. Uh, there we go. The Keeling curve. This scientist named Keeling started to measure carbon dioxide in the atmosphere in an island in Hawaii where the air was so clean, really isolated from industrial sources. And the idea was that that would be a good place to measure carbon dioxide. So he started measuring it every year, and you'll see that there's a sawtooth pattern here. So that sawtooth pattern is because the seasonal variation in carbon dioxide is relative to the amount of organic growth, trees, plants that in the summer in the northern hemisphere or the summer in the southern hemisphere, these plants spring to life. They take in sunlight, they produce chlorophyll, and through photosynthesis, they absorb carbon dioxide and they build it into the plant material. Then in the winter, those plants die off and they release that carbon dioxide to some degree. Now, the northern hemisphere has more land mass than the southern hemisphere. So in the northern hemisphere summer, we take up more carbon dioxide than we do in the southern hemisphere summer. And that's the reason for the sawtooth. So the peaks are the winter in the northern hemisphere, and the troughs of each of these sawtooth patterns is the trough is the northern hemisphere summer. Now I drew a red line in here. That's not part of the normal graph for the Keeling curve to show that's a straight line, to show what a straight line growth in carbon dioxide would be like. And in fact, you can see that it's not linear, it's exponential. And so with each passing year, the carbon dioxide problem gets worse and worse. Now, something I want to point out about this, and it's a bit of disinformation that you'll hear about greenhouse gases, carbon dioxide in particular, is people will say that, oh, the volcanoes put out far more carbon dioxide than humans do. That's false. The truth is it's about 1% of what humans produce. But what I want to show in this chart is you might remember a very massive volcanic eruption in Pinatubo in the Philippines. Now, I don't remember what year it was, but if what they were saying was true, then you ought to be able to see it here. You ought to be able to see it as a big spike in the amount of carbon dioxide in the atmosphere, and you don't. I don't see it. I don't see it at all. All right, going back here to where I was. So the amount of greenhouse gas has, the carbon dioxide has grown since the beginning of the industrial age, about the 1850s or so. And as I showed you, it's been increasing exponentially. And the question is, what does this really mean? Well, that 57 degrees of climate stability of average temperature around the Earth, we reached that point about 10,000 years ago. This chart shows the temperature from the end of the last ice age as we warmed, and we came up to this dotted line, which is the zero mark is the um, I believe it's the average of the window from pre-industrial times. But you see it came up and it stabilized, and then, there was a little bit of adjustment again in about 8,000 years ago. Now, what does that mean? And then it's been declining. We're actually sliding toward the next ice age, or should be if we didn't have climate change. But if you think about recorded history, it goes back about 8,000 years. So over the last 8,000 years, even though humans have existed for far longer than that, um, it was really about 8,000 years ago that we started to become organized into communities, cities, and we began to build the wealth of society on the margins where we could make a living, where we could grow crops, where we had reliable access to water, and all of those natural features define our boundaries. We don't build anything out west to speak of in the desert because we don't have access to water. And that's the way it's been for 8,000 years. And, we build along the coast of the Atlantic Ocean, along the coast of the Pacific, in various parts around the world. We built based on that really stable environment for the last 8,000 years. So that's changing. And so it threatens the wealth of humanity. Now, this chart is just 2,000 years long, and I include this one to show again the remarkable stability of the environment for 2,000 years until recently when we have dramatically changed the amount of greenhouse gases and we have this hockey puck effect, hockey stick effect. And you can see that we're going into unknown territory. What we know about weather and the ability to predict weather, to the ability to have reliable agriculture, it's all based on the past that has been very stable, and the future now is not stable. The future is a huge unknown. This chart is a way of demonstrating the climate anomalies, the temperatures, based on the period from the average from 1950 to 1980. And as this is an animation, and what you're going to see is like a clock going around the months. Every time you go around, it's 1 year. And you're going to see white, meaning stable or average temperature near this green line, which is 0 degree change, 0 Celsius change. And then if it's colder than that, it'll be blue. And if it's warmer than that, it'll be red. So let's take a look at that. And what you see starting in 1880 is that there's variations every year, small variations. But for the most part, we see a lot of white, a pretty stable temperature. You'll see when we get into the 30s, there'll be a warm period that correlates with the Dust Bowl era. But it comes back. It's not real red. It's sort of pinkish, and then it comes back. And now we get into the uh, modern era. And when we get to 1980, you're going to see a dramatic effect. It's suddenly going to get a lot more red. And 1980 was a critical year. As I mentioned earlier, that's when James Hansen appeared before Congress and told them that this is a serious problem and we need to do something about it. Um, Since 1980, the effects of climate change have become larger than the background variability. And so now the question is there any question about what's happening? And as this chart turns to the side, you can see that we had basically a column, a consistent temperature before 1980, but since 1980, it's going out like a water tower. And there's no question where it's going. There's no question about whether this is a temporary effect or a trend that is really threatening. This is another way of looking at temperature anomalies. Many of you, I'm sure, are very understand what bell curves mean. The key thing about bell curves, this is a distribution of measurements of samples, and this bell curve is very natural. Most of the samples are right in the middle, or that's where you have the peak. Above that average is standard deviations of 1, 2, and 3 and more. And mathematically, the bell curve follows a very clear pattern, and that is that within a standard deviation above and below, you have 65% of the samples. Within 2 standard deviations, you have, I believe it's 98% of the values. And within 3 standard deviations, you have 99.7% of the samples. So we have extremes of cold and heat, and they would be out beyond the 3rd standard deviation, but there aren't very many of them. It's 0.03%, 0.3%, sorry. Now, as I start this animation, you'll see 1950 to these are 10-year averages, and you're going to see the movement of this curve toward the hot side. And what's particularly dramatic about this is that now if you look at the 3 standard deviations where 0.3% of the samples were, now that 0.3 is, beyond the 3 standard deviations, that 0.3% has become huge. So we're going to have a lot more anomalies on the hot side, much rarer to have anomalies on the cold side. They're still there, and people will hold them up and say, see, it didn't change because we still have this outlier, but that's very rare to and you can't draw a conclusion from that. All right, so we have this unbalanced energy flow. We have more energy flowing in than we have flowing out until we reach a new equilibrium. We don't know what the weather, what the climate will be like at that new equilibrium because we haven't experienced that in our past. And we keep changing that. So the equilibrium keeps chasing after that changing number. So what does it mean for humanity? And this is where I'm going to spend the least amount of time. But again, to begin with a cartoon, this is a Gary Larson. Again, he's my favorite. He said, "This is it, Jenkins, indisputable proof that the Ice Age caught these people completely off guard." And there's Ugg in the outhouse looking out, wondering what's happening, and it caught him by surprise. We aren't surprised, but we are going to be surprised by new phenomenon and new ways of existing in this world. So first thing I want to mention is Corey Stringer, a Vikings football player who died as a result of practicing in high humidity. Humidity is one of the effects of climate change. The human body cools itself by sweating, and as humidity rises, the ability to cool our bodies becomes more difficult. With the dry environment, humans can survive up to about 124 degrees Fahrenheit for 6 hours. And that's kind of the threshold, 6 hours. With high humidity, the dew point, which is a measure of the humidity, actually a dew point that gets close to the body temperature of 98.6 degrees makes it impossible for us to cool our bodies. We cook our brains. If you can't get out of the heat and humidity into some air conditioning environment, then you're going to die within 6 hours if the humidity rises close enough to the body temperature. And it's actually somewhere around 94 degrees dew point. We've actually had some dew points in the world above that in the Arabian Peninsula area. So it's coming, and that didn't used to happen. Uh, of all the different kinds of effects that happen with climate change, the scientists will give a probability of how likely it was or what percentage factor climate change played in a particular phenomena. When it comes to wildfires, it's a very, very strong correlation. And that is because we get these atmospheric rivers that encourage a lot of growth. That plant material stores that carbon, which is a fuel for fires. Then we follow those atmospheric rivers with drought, and then all it takes is a spark, and you have all of that fuel. You might think that it's the forests that are the biggest problem, and they certainly are a problem, but it's the low growth that grows quickly and dies and provides fuel that is actually a bigger threat. So it's leading to longer fire seasons, more intense, higher amounts of damage from fire, and very strongly correlated. I told you about how if the temperature, the dew point is above, about 94 degrees Fahrenheit, you can't live there. And so it's important to look at what's happening around the world with temperatures and recognize that if you are a society that doesn't have access to air conditioning and ways to escape the heat, or ways to mitigate the effects of drought and variability and rainfall and all of that. If you don't have the ability to deal with that, you're not going to stay in your home community, going to migrate. And migrations, you know, even if there's only one day a year that you can't live there, you're going to have massive amounts of people moving. And we have places like that in the world today that are uninhabitable, in effect, uninhabitable because of climate change. And so that movement causes destabilization of governments as people react to what they feel like is too high an amount of migration. So this is just to highlight a couple of exceedingly hot temperatures that have occurred. And we've experienced some of them. A couple years ago, there was this massive heat dome over the Northwest United States and Canada in that area. Portland broke its all-time record. Many areas in that area of Canada broke all-time records. We also saw very high temperatures in Seattle, Washington. And again, understanding that we've built to a particular climate that we've been used to. You go to a place like Seattle or Portland, a lot of people don't have air conditioning. They haven't needed it. Well, now they do. And so society, here we can change. We can go out and buy air conditioners, but, in some places of the world, they can't do that. But we're seeing much more intense and much more destructive hurricanes. You all know about that. And in particular, I want to mention for our members who are from North Carolina, we experienced some tremendous damage from Hurricane Helene this last year, where the extent of damage from the hurricane was exacerbated by the fact that there was so much rainfall. The rainfall fell before Hurricane Helene, saturated the ground, and then when the storms from Helene came, that moisture in the ground continued to provide fuel for the hurricane. So the hurricane's effects went farther inland, and places that had been somewhat immune from the damage of hurricanes now suddenly found themselves experiencing tremendous damage. And North Carolina suffered greatly from that. This is hail. And I include this one because, a few years ago, we had a lot of flooding in the Middle South. And the fire truck is floating. If we, who's going to save us if the fire truck is floating? And of course, as people of faith, we are very sensitive and aware of our responsibility to people who around the world who are affected by our actions. All right. This animation, and I'm going to play it twice here. This shows the desertification of America from climate change. I'm going to back up here, and I want you to focus on the upper Midwest, Minnesota, where I live, going from being a very moderate climate with a reasonable amount of moisture throughout the year for growing crops, suddenly becomes more drought impacted than any place at the beginning. This is the beginning. There are none of those dark brown areas. And at the end, Minnesota is one of the most drought impacted areas of the country. All right, so